Hello everyone, welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of numerical integration, specifically in relation to the midpoint rule. In this particular episode, we are using the midpoint rule as another powerful numerical integration method for solving, some definite integral problems for which the antiderivative of the integral may be almost impossible to find or to approximate. All right, so stay with me even as we explore that together. And at this point, if you have not subscribed, please do so. Turn on your notification button so that anytime I release new content, you'll be the first to receive that. All right, let's get going. So suppose that we are trying to find an approximate value for this particular definite integral. Okay. And as I mentioned, one of the reasons why we have the numerical integration is that sometimes the antiderivative of the integrand, which case is the f of x, is almost almost impossible or almost impossible or difficult to sort of integrate or even to estimate directly. So in such a situation, we have to rely on another powerful tool known as the numerical integration. Okay. So that's the essence of the numerical integration. But this time around, we are going to use the midpoint rule as one powerful numerical integration, method. So let's get going. So what is the midpoint rule? So with the midpoint rule is just if I may put it in a very nice way, more or less like an add-on on the how do I put it, the Riemann sums. The Riemann sum says that for us to approximate the area under the curve, we need more rectangles to do that. Okay, so within every sub interval, we erect a rectangle on each. Okay, very good. But with the midpoint rule, what happens is that after erecting a rectangle on each subinterval, we are going to find a midpoint on our average or within each subinterval. Then we evaluate the function at that point. Is that okay? So that is what the midpoint rule is talking about. So suppose let's say I give you a graph of, we have a problem as this, and on that search graph, okay, I erect some rectangles here. I erect some rectangles. Suppose I erect some rectangles. Suppose that they are of equal weight, okay? So what the midpoint rule does is that, suppose this is my x1, my x2, my x3, my x4, okay? What the midpoint does is that it kind of find a midpoint within each subinterval, okay? It find the midpoint of the average of each subinterval, okay? Then evaluate the function at these points. Is that okay? So that's what the midpoint rule does. That's what it does. I believe we are all getting it. So what basically I'm going to do is I'm going to pick an example so that we really understand it. And the same thing, we still have to make sure that we know the width. We know the width, and we know that what from so the width. So the width we said is what, b minus a divided by n. The n we said is the number of sub intervals, okay, or the number of partitions, okay. Very good. And so if that is what we're going to do, it means that the midpoint rule or the midpoint formula, we're just going to be our delta multiplying. Now, remember the function, we're going to evaluate remember, we are going to evaluate, suppose this is my A1, okay. Remember, we are going to evaluate, let me just, have another rectangle here. So what the midpoint does is that we are going to find the midpoint of each sub interval, okay? So what it means is that over here we're going to find the average of that, to find the average within this interval, what is that? We're going to add them together, okay? So we add them together and divide it by 2. Is that okay? Then we do the same thing for this. We do the same thing for this sub interval. So we're going to have what? X1 plus x2, then we divide it by 2, okay? Is that okay? So that's how we deduce the formula for the midpoint. And the same thing, we do the same thing for this. We kind of add x2 to x3 and divide it by 2. So f2 and x3 divided by 2. Then we do that until such a time we get to f of xn minus 1 plus the last point, then we divide it by 2. And that will give us, that becomes our midpoint, formula. Okay? I believe that is okay. All right. So this becomes our midpoint, formula. So at this point, maybe I'll pick the same problem as we had in our previous episode to solve a problem. So example 1. So what we are going to do is that we are going to use the midpoint. So use the midpoint rule to find an approximate value of this particular problem. So, all right, so we have this particular problem to solve. We want to use, the midpoint rule to find the approximate value of such integral problem. And in this case, we are using the n equals 6 equal size intervals. Okay. All right. So what we need to do is to look at the width. So the width. So we need to look at the width. Okay. And as just a quick one, remember we said that the midpoint rule, the formula is this, okay? So x1 plus x2 divided by that plus x2 plus x3 divided by 2, up to f of x and minus 1 plus the last term, which is b, all of that divided by what? By 2. So this is the, the midpoint formula that we kind of talk about. So in which case we may need our weight, okay? Our weight is changing x, and we said it's what? B minus a or divided by n. By n in our case is 6, right? And then our b is the upper limit of the integral, which is 3, okay? Which is 3. And then our a is 0, is the lower limit, and that gives us 0.5. Okay. All right. So in such a situation, we kind of say that so with the first sub interval, which is from 0, that will be from 0 to, since we have the weight with that, so it means that's from 0 to 0.5. Then it means that the midpoint, it means that the midpoint, so the midpoint will just be what? 0 plus 0.5 or on 2, and that should give us what? That should give us 0.25. Okay. So at this point, what I want us to do is that we're going to use a table to kind of do all of that. Doing it one by one, I think will take more time than to sort of use a table. So let's use a table. So let's construct a table. So with the table, I'm going to have the sub interval. The sub interval, we are going to use the width. We are going to use the height and then the area. So we have the sub-interval to be so the first sub-interval will be from 0 to 0.5, and then the width we all know will be from here we have the width to be 0.5, okay? And then the height, what then becomes the height. So the height, what happened is that we are, you know, what happened is that within this sub interval, we found a midpoint, and the midpoint we already found it to be what? To be point 25, okay? 0.25. Then we plug that into the main integrand, okay? And then, but then we know that the integrand, we all know that this is the integrand. Is that okay? This is our integrand. So we plug 0.25 into that, and that should give us so 0.25 into the integrand. And that should so e to the power 0.25 plus 1. And that should give us 1.5113. And then the area should be equal to what? Should be the width times then the height. So the width is 0.5, and then the height is what? 1.5113. And that gives us what? 0.75565. Okay. And then the second sub interval is what? 0.5 to 1. So the width we know is 5, and then so with the value for with the value that we're going to use to compute for the height, what happens is we're going to add these two together, okay? So we're going to add these two together. Since we are looking at the midpoint of this within this interval, we add them together and divide it by 2, okay? So we add the 0.5 to 1, then we divide it by 2, and that will give us the midpoint, okay? And that should give us what? 0.75. Then we plug it into the integrand, and that should give us 1.7655. Then we kind of multiply the width and that of the height, and that should give us 0.88275. Then another weight will be then the next sub interval will be from 1 to 1.5. And then the width we all know is 0.5. And then the midpoint of this interval sub interval will be what? Will be 1.25. And then we plug into the integrand, that should give us 2.1190. Then to find the area, we multiply the width and that of the height, and that should give us 1.0595. Then another sub interval, we have 1.5 to 2, and the width is 0.5. And then when we find the midpoint within this sub interval, we should have 2.25. Okay. Is it 2? No, that should be I think they might. That should give us 1.75. Then when we plug that into our integrand, and that should give us what? If you're using a calculator, that should give us 2.5990. And then we multiply this height, and that would we multiply the width and then height, and that should give us 1.2995. Okay. So the width stays the same. Then we take the midpoint of this, and that should kind of give us 2.25. And then we plug into that, and that should give us what? 3.2 385. So the area will be the height multiplied by the width, and that should give us 1.61925. So the midpoint of this gives us what? Gives us 2.75, and that should give us 4.0795. Now all that we need to do is to add all the areas together, and by adding the areas together, we are going to have 7.6564. And this value is slightly, this value is slightly is slightly kind of better approximation of the definite integral, because when you compute, when you kind of run a you use the computer to run the result for this, you should be able to get, for this particular problem, we had I think 7.67 548. So we see that these two values are almost close. Okay, so the midpoint has given us a better, a slightly better approximation of the definite integral. Okay, so another way that I would want to kind of explain this better is to give you a pictorial picture of what we've done, we've had. Remember, the interval was from zero to 3. And then so what that we did was that within the interval 0 and 0.5, we kind of we found the midpoint by adding the two together, by adding the 0 onto the 0.5 and divided by 2, and that gave us 0.25, and we did the same for the other sub intervals. And these are the values that we had. And these values, what that we did was that these midpoint values, what that we did, we plugged them into the integrand. And remember, the integrand is this. We plugged that into the integrand to give us the height. And then the next thing we did was to multiply each height with against so we multiply each height by the width. Okay, and the width in our case we had 0.5. The width was 0.5. So for each height we multiply it by 0.5. Then and afterwards we kind of add all the areas together, and that gave us this particular value. Okay, and then when we compare it to the actual value of the definite integral, we had this. And you see, when you compare these two results, these are very close results, which makes that the midpoint rule is helps to get a better approximation of the definite integral. So at this point, if you have not subscribed, please do so. Like my content, and comment as well, and then also help spread this content to your colleagues, to your loved ones. And we'll be grateful if you continue to do that for us. And also, thank you so much for your usual support. We appreciate you so much. Thank you so much. Bye bye.